Video 3 in our sequence of videos on partial fractions leading up to integration using partial fractions. This one is about some worked examples for distinct linear factors. So consider the question we have there in front of us, or the task: resolve 3x plus 5 over x minus 1, x plus 3 into partial fractions. Firstly, we need to identify which case it is. Well, it's case 1. Case 1, as you can see, is where we have distinct linear factors. Okay, so let's see how that works here with this particular example. Thus, for ax plus b, we've got 3x plus 5 on the numerator. For x plus 2, we've got x take 1 in its place. X plus d, we've got x plus 3 in that place. Thus, we would have partial fractions in this form here. Okay. Now, in order for us to have equal denominators, or equate the denominators, they need to be the same. That way we can just concentrate on the numerators. So what I mean by that is we'd like x minus 1, x plus 3 on both sides. So what that would mean is that we have a on the numerator, but it has to be multiplied by x plus 3. And we also have b. It also needs to be multiplied, this time by x minus 1. Then we can come up with this statement where we've got, if these things are equal, the denominators are equal, the numerators must be equal, but we've got a couple of unknowns there, so I'm just going to call that equation 1. Now, we do this because it helps us solve things more easily. We would have some problems here because some values of x on this line back here are not valid. So x cannot equal 1 and negative 3. Okay. But on this line, that's true for all real values of x. Now, if we consider the null factor law for a moment, and we find the roots of x minus 1, x plus 3, we'd be looking at x equals 1 and x equals negative 3. Now, this is a good little strategy to help us solve what we've got. You don't have to use these values, but we know, because we're only looking at the numerator, we can use any real values. Well, let's use when x equals 1, and let's use when x is equal to 3. So, let x equal 1. So on the left-hand side, we'd have 3 by 1 plus 5. On the right-hand side, we have a outside of 4 plus b outside of 0, which is just 0. So on the left-hand side, we've got 8. And on the right-hand side, we've got 4a. So a equals 2. So we know the value of one of those missing parameters. We now repeat with x equals negative 3. Left-hand side. On the right-hand side, we've got 0 times a, which is 0, and we've got b times negative 4. So we have negative 9 plus 5, which is negative 4, equals negative 4b, so b equals 1. So the given expression, we can resolve that into partial fractions now. So instead of a, we can actually write 2, and instead of b, we can actually write 1. In the near future, we're going to look at examples where we integrate expressions like this, of course, and you can see perhaps from what we've studied already in integration that those two things could be integrated fairly easily based on what we know already. Now, it is true that we can extend case 1, distinct linear factors, into this form here. So we only had ax plus b on the top, but we really could have f of x on the top, some function of x, and instead of just x plus c, x plus d form, we could have these linear factors which have a coefficient with the x, coefficient other than 1. And it would be true. So this is a slight extension, but the pattern is exactly the same. So a very mild extension on what we saw previously in previous video or two. So let's do an example of one of these. So let's resolve what we see here into partial fractions. Now we see we have some sort of quadratic on the top, and we have a cubic, if you look closely, on the bottom. And we can see that it does fit the form, the extended form of case 1 there, but no longer do we just have something like ax plus b on the top. We have something of a higher order, but it is still a proper fraction, and so it still fits the description that we've been using. Now, basically speaking, from an early video on this, we saw that for every distinct linear factor on the denominator, we have a separate term in the partial fraction expansion. So if we look at the denominator here, we have 1, 2, 3, not 2 now, we have 3 distinct linear factors. So we will see that when we write this out, we'll have 3 terms summed together on the right hand side. So let's go ahead and do that. So x plus 1 on the denominator there, so we have b, and x minus 2 on the denominator. We have c. You see? Do you see? I hope so. It's just a slight extension, okay? Now if you're doing, things akin to this video, you must be awfully good at fractions. You really need to be. And here's another example of why. So if we want to use that same strategy so we can make the denominators the same on the left and right, so we can equate the numerators because everything else is equal, we have to deal with 3 terms on the right hand side. Okay, let's have a look at that. Okay, so looking at the first term here, we have a over x plus 1, but a needs to be multiplied by x minus 2 and also x. b over x minus 2 also needs to be multiplied by x plus 1 and x. c over x needs to be multiplied by x plus 1, x minus 2. Okay, so we have equated numerators, and we are equating the numerators. You might think, oh no, this is going to be like simultaneous equations and so on, but no, it's not. We don't actually have to go there if we don't want to. And again, think about the roots of this cubic here. So that'd be x equals -1, x equals 2, and x equals 0. So we can use them no problemo. Okay, let's just worry about the numerators now. So we'll write that out like so, and let's start at, I'm going to start with that one because it's nice and simple. You watch this. This is pretty cool. So let x, I said one of those roots is 0. So let x equal 0, because remember it can be any real number. This line here is true for reals, because we've gotten rid of the complication of the denominator on the line above, you might recall. So let x equal 0, so that's 0 takes 0 minus 4, which is -4. The first term here involving a will be 0, because x equals 0 due to that term there, the whole thing, null factor. So 0, and the middle term due to that, 0. The third term involving c, we have c times 1 times negative 2, which is no big deal. Okay, so we have negative 2c equals negative 4, so c equals 2. So we've got one of our parameters, 2 to go. If we choose the next one as x equals negative 1, we sub it into the left and we sub it into the right. So we have a outside of negative 3, sorry, it's a 3, negative 3 times negative 1. Now, the other two terms go away because the term involving the b will come out as 0 even if you have to pause to have a look. It's the same reason as we just saw, and same with c. And this happens with all of them. It's great, isn't it? So we've got 2 by 1 is 2, minus negative 5 is 7, minus 4 is 3. And that equals 3a. So a equals 1. Lastly, let x equal 2, so we sub that in. Term involving a comes out as 0 because one of the factors is 0. And then we've got b times 3 times 2. And the third factor contains a 2, contains a x minus 2 factor, so that'll come out as 0 as well. So we have 4 times 2 is 8, 8 take 10 is negative 2, negative 2 take 4 is negative 6, equals 6b. b equals negative 1. So we've resolved that into its partial fractions.